By the end of this video, I'll expect you to understand the meaning of a reflexive relationship, explain some of their common applications, and the typical paths of evolution to other shapes. In English grammar, a word is reflexive if it refers back to the subject of the clause in which it is used, like myself or themselves. A reflexive relationship connects an entity to itself. We read it exactly the same way as a normal relationship. We choose a label, follow the path of the relationship, and look for a chicken foot at the end of the path. An employee can manage many employees. An employee can be managed by one employee. Here are those statements written out. This is a one-many reflexive relationship, which is the most common type of reflexive relationship. In this example, we're applying it to the use case of data in the shape of a tree or a hierarchy. Notice that as before, the degrees on these links are up to one and up to many. This model does not say that each employee must have a manager. For example, John has no manager. The model says that each employee can be managed by at most one other employee. It also does not say that an employee must manage any employees. Corey and Derek and Becky in this example manage no one. Finally, by combining those two ideas, notice that it does not say that any given employee must relate to any other employee at all. Kevin here is neither a manager nor is managed. Perhaps he's running his own startup as a one-man show. Can we think of other applications of a one-many reflexive relationship? How about a comment tree? Here, a comment can reply to one other comment as context, and it can be replied to by many other comments. Really, just about anything you can imagine with a pattern like a tree, a hierarchy, taxonomy, or a fractal can be modeled this way. Much less common, but also valid, is a one-one reflexive relationship. This particular model fragment describes a queue of items. Each queue item can precede a queue item and can be preceded by a queue item. In the example below, the number 12 precedes the number 7, and the number 7 precedes the number 31. Like before, we're not saying each queue item must be preceded by anything, as 12 is not. And we're not saying that each queue item must precede anything, as 31 does not. Nor are we saying that these must be connected at all. Queue item number 42 is neither preceding nor preceded by anything. Finally, I will point out that there are many ways in computer science to implement lists, whether using memory arrays, linked lists, or hash tables. And we're not prescribing any of those technical details with this notation. The numbers here illustrate just one example of the kind of data that users might want modeled, and the kind of data that this model can represent. Finally, you can probably guess what I'll show next. Reflexive relationships can indeed be many, many. What are some use cases of this? One common one would be a social network. Here, each person can follow many other people, and each person can be followed by many other people. To represent this kind of data, it's usually easiest to draw dots in a circle for your people so that you have open space to create instances of the relationship in between, including some cases where two people follow each other, and some cases where people are either not following anyone, like Corey, or not followed by anyone, like Lisa, or neither, like Derek. As before, a social network is just one kind of data that we can model with a many-many relationship. Another example might be a map of standard flight paths between airports. You can imagine each of these dots as an airport and each line being a flight path. It should come as no surprise that many reflexive relationships follow exactly the same path of evolution as normal many relationships. We will actively evolve away from this shape, remove this relationship, and replace it with an intersection entity. So this type of relationship is allowed to exist, but if you discover one, you will want to go through the next steps of the flow. So we can create a dedicated entity that represents the relationship, and it is identified by two people. As before, this is one of those intersection entities where it's tricky to come up with a name, but let's suppose the users decide it is called a follow. As we seek descriptors for follow, we might discover that about each follow we also want to remember its created date. Now, do you see a problem with this LDS? The problem here is that we have two exact copies of the same relationship. We're saying that for each follow, we can remember a person, and a person. Well, which is which? This is considered a syntax error. One of the syntax rules is that between any pair of entities, there is at most one unlabeled relationship. That allows us to tell the difference between the two of them, or however many there are. Now that we have two relationships between the same pair of entities, we must label at least one of them so we can tell the difference. Whether just one of them or both of them need labels will be determined by how the users talk about them. Here's an example of what that might yield. For this particular model, the abstractness of follow also made it pretty difficult to come up with the labels. It requires explaining a follow as its own thing, which is not something we generally do. But the challenge of labeling revealed some interesting concepts. If we think of each arrow here as a follow, we can describe the way that it connects to people. A follow can target a person. For example, there are two follows here targeting Corey. And a follow can be aggregated by a person. For example, John's personal feed is an aggregation of content from Corey and from Becky. Getting to this level of understanding can reveal a lot of hidden detail in a data model. Again, this video is about reflexive relationships. And a shape like this is where you would expect to end up if you found a many-many reflexive relationship. Now check your understanding.